Okay, algebra, we are going to create our graphic organizer for chapter 8, exponents and exponential functions. And make sure your name is on the front page of your graphic organizer in case it gets dropped somewhere. Okay, there might be other ways you could chop up the chapter, but in the 4 regions here inside your book, the first thing we did was we just reviewed. Before we got into exponential functions themselves, we just reviewed expressions, right? So we were looking at the properties involving products, exponent properties involving products. Products represents what operation? Good, multiplication. So after exploring the properties involving multiplication or products, we went to exponent properties involving, say it out loud. Quotients. Good. Division, which is under the category of quotients. So once we explored all of these things, we could start getting into equations, right? There were a couple of other things that we did. We have those too. If you need to pause the video, do that. Okay, and then in the third category I have here, we dealt with the special exponents, the zero and negative exponents. And there's a type of notation where we always find powers, or which include exponents. What kind of notation always has that? Good. So that's under here. So just kind of the special use of zero, negative exponents, and scientific notation. And then we got into the exponential functions, right? Which involve 2 major types, exponential growth and decay. So pause the video and take it down. Okay, so let's look at the exponent properties involving products. The first property was called the product of powers. So it looks like multiplying powers of the same base. Here it is as a rule. A to the n times a to the m. And can you finish the rule? Hey?
A to the m plus n.
Good. And there's a little sample for you to complete. Z to the 3rd times z to the 5th times z to the 5th. Equals, let's say it, z to the
13.
Good. Then we have the power of a power. So can anybody remember what that rule looked like from the start of it? Power of a power. A, what? A to the, Madeline? A to the, we're going to use m and n for our exponent. And actually, that would be this, product of powers. A to the m times a to the n. You know what I'm saying? So a power of a power is a to the m to the, right, so there it is, to the n. So you're taking and putting an exponent on that entire quantity that already had an exponent. So once you do that, what does it look like, Cassandra?
A to the m.
Good. Multiplication. Multiplication of those exponents. So negative 7 to the 4th, that whole quantity to the 4th is what, Haley? Good. Negative 7 to the 16th, which because that's positive could be written as negative 7 to the 16th. So we had the product of powers, power of a power, and then we end up with the power of a product. Okay? So here's the power of a product. And tell us what this looks like, Jack. If you have AB to the n, you
have A to the n times.
Good. So each of the factors has that exponent.
It's negative 8 to the 2nd. Oh, wait. Yeah.
What is 8 to the 2nd?
60, negative 64.
So you could say negative 64.
Okay, you just say 64.
No, because the negative in this case is not being affected by the exponent. So the answer here is, finish it for us, negative 64 what?
Times x squared, y squared.
Good. Now, this negative is outside the parentheses, so it is as though we're multiplying 64x squared y squared by a negative 1. So it's not in. And that's it for properties involving products. And properties involving quotients we'll do, and then we'll stop here today and finish it tomorrow. Okay, so that you can get a head start since we have 2 days of review. But involving products, we have the quotient, oh, I gotta hide that. We have the quotient of powers. So just a second, let me hide that. Quotient of powers dividing of powers. What does it look like then? Anderson, what does it look like?
It'd be a to the n minus 1.
Good. Subtract the denominator exponent from the numerator exponent. And then if your expression still has a negative exponent, you may not leave it that way. You must have positive exponents in your answers. That's a rule of exponents. So in this example, you don't have to move anything. 17 to the 12th over 17 to the 8th equals 17 to the?
4.
Good. So you just subtracted, and the answer was to the 4th. Okay, and then we have the power of quotients. So this was dividing, quotient of powers is dividing powers. Power, raising a power to a quotient. So you have a fraction being raised to a power here. So how do we finish the rule here? Vivian? Good. A to the m over b to the m. So it feels like we're spreading that exponent to each of the factors in the fraction. So who can finish the example? Tom?
We're going to x to the 10th over y to the 4th.
Good job. Okay. So each term has been squared. Okay. Okay, let's take a look at the third section of Chapter 8's graphic organizer, zero and negative exponents, and our scientific notation. So let's take a look at zero and negative exponents first. Okay, what must you remember when anything is raised to the 0 power? It equals 1. Okay, so and then when it comes, now what is the number one mistake? Anything to the 0 power? A 6th grader would say 0. But when we know, we've proven that a to the 0 equals 1 in your notes. So go back and take a look at that. For instance, a to the first over a to the first, we would subtract those exponents and end up with a to the 0, which is 1. Any number over itself is 1, right? Okay, so now a to the negative n. We know that a negative exponent is about location. So a to the negative n equals 1 over a to the n, right? If your negative n is in the denominator, we move that to the numerator, okay? So we have 3 to the negative 4. And it's not coming up for you on the screen, is it? Okay, so Kate says 1 over 3 to the 4th. And 3 to the 4th is simply 3 times 3, which is what? 9. And then you have 2 9s, don't you? So 9 times 9 is? So 181. 181st. Okay. And we have a second example, a quotient to the negative 3rd, or 3 over 5th to the negative 3rd. So Aaliyah, what would you say that is? What would you do if you have 3 over 5 to the negative 3rd?
You multiply 3 times 3 goes on.
So this is the third. So you could say 3 to the negative 3rd over 5 to the negative 3rd, right?
Mm-hmm.
But the negative tells you to do what with that term? No. It's about location, remember? Look at, when we have a to the negative n, it equals 1 over a to the n. It's about moving it to its inverse location. When it's in the denominator, we move it up.
So you just switch it?
So in this case, good, we're going to switch it. So we have 5 to the third over 3 to the third. Okay? Do you remember what 5 to the third is? 5? Good. 5 times 5 times 5 is 125. And 3 to the third? 3 times 3 times 3.
27.
Good. 27. And we could change that to a mixed number if we wanted, right? Okay. And then the final little section under here is scientific notation, right? So what must a number look like if it's in scientific notation? Kate?
Like a lot of zeros.
Well, there might be a lot of zeros, right? Or it might have been a number with a lot of zeros, a big, huge one, and you're changing it to a number times a number, right? It's a power of 10, okay? Remember that the first number, C, must be a value between 1 and 10. It can't be 2 digits, right? So let's see if you can put these numbers into scientific notation. What is 463,000 in scientific notation? Leah, you know?
What?
463,000.
You move it over, you move the decimal over 5 places.
5 places, so you end up with
4.63.
times 10 to the,
That.
you took away 5, so give 5 back. Good job. Okay, Kate, how about this one?
You move it over once, so you get 3.47 times 10 to the first. Well,
You gave it one place
Oh,
value, so
okay.
take it away. Good job. Okay, and then when you have scientific notation being multiplied, what property could we use?
you like just distributed.
Actually commutative,
Oh.
right? Because it's all multiplication. So we can just multiply the two factors 3 times 4, which is 12. And we can multiply 10 to the 6 times 10 squared, which is
10 to the 8.
good, 8. Okay, but is that scientific notation? 12 times 10 to the 8?
You have to move it over once.
Good, so we got to take away 1 and give it back. So 1.2 times 10 to the 9th term. Good. Okay, when it comes to dividing scientific notation, we can do it in parts again because these are all factors, right? So what is 1.4 divided by 7?
2.
0.2, good, 0.2 times 10 to the 3rd over 10 to the 2nd is what that's supposed to say.
The 10 to the first.
Good. Now is that scientific notation?
Yes.
Actually, this first number, 0.2, is not a number between 1 and 10.
Oh.
So we'll give it a place value,
Oh, I thought it was.
and then we'll take 1 away, right?
10.
To the 0. Isn't that weird looking? 10 to the 0. What is 10 to the 0?
2.
What'd you say? Oh, you're giving me the full answer. But 10 to the 0 is just
Oh, 1.
1, and then 2 times 1 is
Oh, yeah.
2. Exponential growth and decay, a lot to pack into 1.5 minutes here. Okay, so we have a model for exponential growth and decay. What is it? Y equals,
A, B, and the X.
good job, AB to the X. Remember that this term A is your y-intercept. Basically, when you stick a 0 into the X, out comes your A, okay? So B is the factor that is being repeatedly multiplied by, as we saw in our tables. Okay, so let's write the equation for this. What is there repeated multiplication here?
Yes.
Times what?
3.
2.
Times 2, times 2, so that's your B. Okay, and where's your A?
0.
On the 0.
Right here, 15, that's your A. So we can say Y equals
A,
15 times
B, to
2
2
to the X, okay? You were finding A again. Okay, so here is the overview of graphing. Remember, we just use a table, find points, and we graph. The growth ones look like this, right? Decay is looking like this. And that's about all the time we have. So, good luck.
Bye.